A fully loaded jumbo jet can weigh about 400 tons. In level flight, gravity has not switched off. The aircraft stays up only by pushing something else down. That something is air. You can see the disturbed air in smoke, clouds, and the wake. But how does a smooth wing make that happen? In the last episode, we cleared away the equal transit story. Air going over and under a wing does not have to meet again at the trailing edge. But the real observations remain. Air above the wing speeds up. Pressure above and below differs. And the flow behind a lifting wing bends downward. Now, look at the whole aircraft, flying straight and level. Gravity pulls down continuously, yet the aircraft does not accelerate downward. The air must therefore exert an equal upward force. If the air is pushing the aircraft upward, what must the aircraft be doing to the air? Hold that prediction. In a smoke tunnel, the answer is visible. Lines approach the wing horizontally and leave with a downward component. The flow has changed direction. The wake is simply the air left disturbed behind the aircraft, like the trail behind a boat, but in 3 dimensions. Above a cloud layer, that wake can carve a descending trough. Near the wingtips, some of the flow rolls into 2 trailing vortices. Between and around them, part of the wake moves downward. That downward moving part is called downwash. Downwash is not a narrow blast like rocket exhaust. A wing influences a broad region of air, giving a large mass a relatively small downward velocity. The air need not reach the ground. The exchange happens at the aircraft. The wake can then spread and mix, but the aircraft has already received the opposite impulse. Our prediction survives. A level aircraft leaves downward moving air behind it. Now we must connect that moving air to the aircraft's weight. Imagine drawing an invisible accounting box around the whole aircraft and the nearby air. Air crosses into and out of this boundary. We do not need to follow every molecule. We compare what enters with what leaves. The incoming flow has no net downward momentum. The wake leaving behind the aircraft does. Momentum is mass multiplied by velocity. For a continuous flow, force depends on how much air passes each second, multiplied by how much its velocity changes. That gives us 2 ways to make the same force. Move a small amount of air downward quickly, or move a large amount slowly. The second bargain is usually more efficient. A broad mass moving downward modestly leaves less wasted energy in the wake than a narrow stream moving violently. Return to the complete aircraft. In steady, level flight, lift equals weight. So the aircraft gives the air downward momentum at a rate numerically equal to its weight. This does not mean 400 tons of air every second. Tons measure mass. Weight is force. The correct balance is air per second, multiplied by its change in downward velocity. That is where the weight goes, into a continuing momentum exchange between aircraft and air, not a static cushion underneath it. This is Newton's third law, applied to 2 different objects. The aircraft exerts a force on the air. The air exerts an equal and opposite force on the aircraft. One force acts on the air, the other acts on the aircraft, so they do not cancel. Hold a flat hand outside a moving car and tilt its leading edge upward. Your hand is pushed upward and backward while it redirects air downward and rearward. Your hand is a crude, draggy wing, not a complete model. But it lets you feel the exchange. Change the air's momentum one way, and it changes yours the other way. If we knew the complete momentum pattern, we could calculate the net aerodynamic force. If we knew the force, we could state the total momentum change required in the far wake. But Newton does not draw the pattern. The third law alone cannot tell us exactly where the air speeds up, where it turns, or how much lift a particular wing will generate. It closes the total ledger without filling every local entry. The wing pushes air down is true, but it is the beginning of the explanation, not the end. One of the strongest controls on that momentum exchange is angle of attack. Now zoom into one slice of the wing. Angle of attack is not the nose angle to the horizon. It is the angle between the wing's chord line, an imaginary line through its profile, and the oncoming relative wind. An aircraft can fly nose-high while descending, or nearly level while climbing. A gust can change the relative wind before the aircraft's attitude changes. Pitch and angle of attack are related, not identical. Now hold the wing shape, airspeed, and configuration constant. At a low angle of attack, the wing produces one pattern of turning and one amount of lift. Increase the angle while remaining below the critical angle, and the surrounding flow is changed more strongly. The lift coefficient generally rises. The wake receives a greater downward momentum change. This is why the tilted hand demonstration feels so immediate. Rotate your hand slightly, and the force changes at once. But there is no magical lift dial. The controls influence angle of attack through attitude and flight path. Speed, load factor, configuration, and gusts also matter. The same pitch attitude can produce different angles of attack. Increase the angle too far, and the flow can no longer remain attached in the same way. Lift stops following the simple trend. That failure deserves its own episode. Below that critical angle, more angle asks for a larger momentum change, and that request carries a price. Look at a real wing from behind. Air curls around each tip from the higher pressure region below toward the lower pressure region above, forming trailing vortices. Those vortices induce downward flow at the wing. The local air meeting each section therefore arrives angled slightly downward from the undisturbed free stream. Aerodynamic force is defined relative to that local flow. Tilt the local flow downward, and the force produced by the wing tilts slightly backward. The upward part is lift. The rearward part is induced drag. This drag is created by making lift. It is neither skin friction nor blunt resistance. It comes from the three-dimensional wake of a finite wing. The momentum picture makes the design consequence intuitive. To support the same weight, you can spread the required momentum change across more air, giving each part a smaller downward velocity. That leaves less kinetic energy behind in the wake than concentrating the change into a smaller mass moving downward faster. This is one reason long, high aspect ratio wings can be efficient. A glider's span helps distribute lift broadly and reduces the induced drag penalty. The wake is therefore more than proof that lift exists. Its width, velocity, and vortex structure tell us something about the price the aircraft pays to remain aloft. Far behind the aircraft, the account closes. The wake carries downward momentum at the rate required to balance weight. But notice what we assumed. The wake pattern was already there. We did not derive that pattern from the wing. We did not predict the upper surface acceleration or calculate the force distribution across the skin. Momentum accounting reads the completed flow from a distance. It tells us what the whole pattern must add up to, not how the wing creates that pattern nearby. That nearby interaction happens at the surface. Air pushes on most conventional wings mainly through pressure acting normal to the surface, with a smaller contribution from shear. Downward momentum, surface pressure, local speed, and circulation are therefore not rival causes. They are connected descriptions of one organized flow. The wake records the consequence across the atmosphere. Pressure records the force across the wing. The velocity field connects them. So what pressure pattern produces the upward force here and the downward momentum over there? We can now answer our opening question. In steady level flight, the aircraft gives the air downward momentum at a rate equal to its weight. The wide wake moves down. The aircraft is pushed up. Newton makes that accounting exact. But air can push on an aircraft only through forces at its surface. Pressure above and below the wing differs, and the air over the top really does speed up. Those are not rival explanations. They are the local machinery creating the momentum change we followed. So what does pressure actually mean? And how can less of it above a wing help hold an aircraft up? That is next.